The International Space Station has circled the Earth for 25 years now, a floating laboratory where gravity disappears and science rewrites itself. From growing perfect protein crystals to understanding how the human body survives in space, the ISS has been the testbed for living off Earth. Some people believe we've learned enough we really are ready to take those next steps, to the moon and to Mars. But are there fundamental challenges in physics, biology, and engineering that could stop us? That's what we're here to dive into. I'm Ben, this is Physics or Bust. The ISS isn't just a home in space, it's the most expensive physics experiment ever built. Okay, CERN does come pretty close. In microgravity, everything behaves differently. Fluids don't flow, flames don't rise, and particles form patterns that can't exist on Earth. When convection vanishes, the laws of fluid motion reveal their deeper truths. That's why the ISS has been a goldmine for material science, developing alloys and growing crystals that gravity would distort on Earth. These experiments aren't just academic. They've improved semiconductors, cooling systems, and even helped design better turbine blades, all from data gathered from orbit. The station's science spans biology, material science, Earth observation, and even atomic physics. NASA has cataloged decades of breakthroughs that show that microgravity research translates into real-world benefits. We'll dig into the physics in a minute, but first, if you like this video, you'd probably like this book. I've got a link in the description below. I do get a small commission, but it wouldn't cost you any extra. Here's a quick breakdown of the ISS discoveries that have changed what physicists and engineers do. Protein crystallization and drug design. In microgravity, protein crystals grow with fewer defects. That provides cleaner diffraction patterns and can be used to produce better models for drug design. For certain targets, space-grown crystals have revealed active sites more sharply than Earth experiments ever could. Human physiology, including long-duration biology and the twin study. A big question for Mars mission is, how does the human body cope away from Earth for years? The twin study, Scott Kelly's year in orbit compared to his twin on Earth, produced a multi-dimensional dataset showing how gene expression, immune markers, and other biological systems adapt and recover. The results are both encouraging and sobering. Many systems rebound after return, but radiation and immune changes remain a concern for longer trips. Fundamental physics. Cold atom experiments in microgravity let researchers trap ultra-cold atoms for longer and study quantum behavior with less disturbance. At those temperatures, quantum physics stops being theoretical. It becomes visible. Scientists are literally watching quantum matter drift in zero-G, free from the pull of Earth. Combustion and fluid physics. Combustion behaves dramatically different without convection, giving us tiny soot formation and altered flame shapes. Experiments with combustion on the ISS taught us how to design safer engines and more efficient burners, and gives insight for future life support systems. Technology demonstrations also. The ISS is a perfect place to test tech that a Mars mission will need. Autonomous software, edge computing, radiation-tolerant electronics. Recently, prototype data center hardware and edge computing software were tested on the station to see if servers can operate reliably in orbit. Finally, Earth observation and climate science. The ISS is a unique platform for continuous Earth observation, being able to monitor fires, crops, ocean color, and atmospheric chemistry, data that directly feeds climate science and disaster response. Beyond physics and labs, the ISS is a diplomatic machine. Agencies from the US, Russia, Europe, Japan, Canada, and more all share hardware, experiments, and even chores. This international partnership has endured a lot of political ups and downs, proof that science diplomacy actually works in orbit. And it's been resilient. The systems on the ISS have been patched, upgraded, and reinvented multiple times, from gyroscopes to communications to even life support, proving that long-duration engineering in orbit can be maintained and upgraded despite international barriers. That operational experience is one of the station's most valuable legacies. The ISS taught us how to live and do real science in microgravity while crossing cultures. But the ISS is scheduled to be decommissioned in a few years, so what comes next? What laboratories will be in orbit, and what knowledge do we still need to get us to the Moon and to Mars? NASA plans to transition low Earth orbit operations to commercial partners while maintaining exploration beyond LEO. Axiom Space is building modules that will initially attach to the ISS and later become an independent commercial station. There's other companies that are building independent commercial stations, and they're all acting as a commercial bridge for research, manufacturing, and astronaut training. So why does that matter for Mars? Commercial LEO stations will scale up in-orbit manufacturing, test long-duration life support systems in a customer-driven market, and provide continuous access for biomedical experiments and hardware validation. Think of them as accelerated market-funded R&D labs that the big science missions can buy from. Now the big leap. First to the moon, then to Mars. NASA's Gateway, a smaller outpost that will be in a near rectilinear halo orbit around the moon, is being built to support Artemis lunar surface missions and to act as a stepping stone for deeper exploration. To turn the idea of a round-trip mission to Mars into a reality, engineers have a lot of physics-heavy problems to handle. Here's what I consider the 5 biggest technical developments that have to be advanced. Number 5, autonomy and robotics. On Mars, there's going to be communication lags that mean that crew and habitat systems need to be more autonomous. The ISS is already testing edge computing and automated platforms, but this tech needs to be scaled into habitats that can self-diagnose and repair, utilizing robotics for repair. Number 4, propulsion and transit architecture. Delta V is expensive, but to reduce transit time and radiation exposure while getting to Mars, we need better propulsion that can give a continual thrust to cut down on that transit time. A couple options would be thermonuclear or high ISP electric propulsion systems. Some of the hardware for those kind of systems are going to need to be validated on a LEO station, whether it's the ISS or one of the commercial ones coming up. Number 3, long-duration human health. The twin study, along with many ISS medical experiments, show recovery and adaptation patterns. But Mars will mean months, if not years, of isolation, a change in circadian rhythms, bone and muscle loss because of the lower gravity, as well as an unknown amount of immune and cognitive effects. We're going to need effective countermeasures, such as optimized nutrition and exercise, as well as possibly needing artificial gravity. Number 2, resource utilization. Mars missions can't haul everything from Earth. Right now, the ISS recycles 90% of its water, but a Mars mission is going to need to not be refilled for years. Closed-loop systems for air, water, and waste need to be scaled and hardened. Plus, on both the Moon and Mars, we're going to need to do in-situ resource utilization, or ISRU. That involves things like extracting water, producing oxygen or fuel from local resources. ISRU is essential for reducing mass and cost. The engineering lessons from the station's environmental controls and life support systems feed directly into those designs. And number 1, radiation protection. Beyond Earth's protective magnetosphere, cosmic rays and solar particle events dramatically increase radiation doses. They need lightweight but effective shielding approaches, better forecasting of solar storms, and countermeasures for if a CME comes their way. Data from ISS radiation monitors and biological experiments help set exposure limits and test protective materials. So what technical development do you guys think will be the last one that we solve? Let me know in the comments below. If you boil it down, the ISS taught us 3 practical lessons that'll help us reduce the risks for moon missions and Mars. Operational experience, how to maintain complex systems for long term, validated countermeasures for human health, and a proving ground for technologies like 3D printers and radiation sensors that have to work far from Earth. We've at least got the stepping stones laid out. The ISS has shown what's worked already. Other LEO commercial enterprises will scale it up. Gateway and the lunar base will test it on or around the moon. And then we have our next big leap to Mars. Now when it comes to the technical developments, the one I think we'll have the most trouble with is the radiation exposure, because the sun is unpredictable. And even though we have a bunch of satellites watching the sun constantly now, if a CME were to come their way, I'm afraid that we'd end up with cooked astronauts landing on Mars. Because you would have to have extremely thick and heavy shielding in order to protect against a CME, or you'd have to be producing an extremely large magnetic field. Plus, once the astronauts are even on Mars, Mars doesn't have a very big magnetic field itself, so we'd have to have some sort of long-term radiation protection for them while they're on Mars. The ISS at 25 isn't an endpoint. It's a running laboratory and a human story. On it, we've learned how to survive, how to collaborate, and how to turn physics into useful technology. The next 25 years will take those lessons and push us even further. Commercial hubs in LEO, Gateway and the lunar base, and the first humans on Mars. The path is hard and has a lot of hurdles, but at least the roadmap is clear. For more space and science news and updates, remember to like and subscribe. And to help this channel grow and reach more people, go ahead and click into this video right here. I'll see you guys on it. And remember, keep asking questions. I'll see you on the next video.